Successful implosion demands structural failure initiation within a 400 millisecond window. Exceeding this tolerance risks lateral drift, resulting in catastrophic damage to adjacent properties. The primary business risk is not the cost of the explosives, but the specialized liability insurance premiums, which often exceed 10% of the total project budget due to the high consequence of failure. Engineers must guarantee the structure folds into its predetermined footprint, typically 1.5 times the height of the structure. This precision is the core value proposition distinguishing implosion contractors from standard mechanical demolition firms. Failure to achieve this controlled collapse immediately triggers multi-million-dollar litigation and potential criminal negligence charges against the lead engineer and the contracting firm. Before charge placement, engineers utilize Finite Element Analysis, or FEA, to model the structure's response to specific load path interruptions. This simulation identifies the minimum necessary charge mass and the exact location required to initiate plastic deformation in critical columns. FEA models predict the dynamic stress distribution during the collapse sequence, ensuring that the structure's center of gravity remains within the foundation perimeter as it descends. This analysis dictates the sequencing plan, establishing which columns must fail first to create the necessary rotational moment. Incorrect modeling leads to pancaking, or worse, uncontrolled directional fall, negating the entire purpose of controlled demolition. Implosion relies heavily on the Munroe effect, utilizing shaped charges to focus explosive energy into a high-velocity jet capable of cutting steel or crushing concrete. Linear-shaped charges, typically containing RDX or PETN, are used to sever structural steel beams and columns cleanly. These charges create a focused pressure wave exceeding 100 kilobars at the point of contact. Conversely, bulk charges, often containing dynamite or specialized slurry explosives, are used for crushing reinforced concrete columns, relying on brisance and gas expansion rather than directional cutting. The selection of the explosive type and liner material, such as copper or aluminum, is determined by the target material's yield strength and density. Charge placement focuses on interrupting the primary load path, specifically targeting the lower floors where the structural redundancy is lowest. Typically, charges are placed on 80% of the columns on the designated fall floors. These floors, usually the basement, first, and second levels, are pre-weakened by removing non-load-bearing elements to maximize the explosive effect. Secondary charges are often placed higher up to ensure the upper structure breaks into manageable pieces upon impact. The goal is not to destroy the columns completely, but to initiate instantaneous brittle failure, ensuring the structure loses its vertical support simultaneously across the entire footprint. Detonation sequencing is managed by highly precise electronic delay systems, which offer timing accuracy down to the microsecond, far superior to traditional non-electric shock tube systems. These electronic detonators are programmed to fire in a specific pattern, often starting at the center columns and moving outward. This creates a V-pattern collapse, pulling the exterior walls inward and minimizing debris scatter. The delay between floors is critical, typically set between 10 and 50 milliseconds, ensuring the upper structure applies downward force on the failing lower structure, accelerating the controlled collapse and preventing outward projection.
The economic justification for implosion rests on time savings and reduced labor costs compared to mechanical demolition. A large structure that might take 6 months to dismantle conventionally can be imploded and cleared in 6 weeks. While the upfront cost of explosives, specialized labor, and permitting is high, the reduction in site occupation time significantly lowers overhead and accelerates the client's return on investment for the new construction phase. Implosion is generally cost-effective for structures exceeding 10 stories or those located in dense urban environments where mechanical methods pose unacceptable noise and dust pollution risks over extended periods. Implosion projects face stringent regulatory oversight from the Bureau of Alcohol, Tobacco, Firearms, and Explosives regarding explosive storage and handling, and from OSHA concerning site safety. Local jurisdictions mandate comprehensive vibration monitoring plans. Seismographs are placed on adjacent properties to record ground vibration velocity, which must remain below established thresholds, typically 0.5 inches per second peak particle velocity, to prevent structural damage claims. The contractor must submit detailed blast plans, including charge weights and delay times, to regulatory bodies weeks in advance, often requiring public hearings to address community concerns regarding noise and dust mitigation. Implosion contractors require specialized, high-limit general liability policies, often exceeding $50 million per occurrence, specifically covering adjacent property damage and pollution liability. Standard construction insurance policies exclude coverage for damage resulting from explosive use. Insurers require exhaustive documentation of the pre-blast survey, which involves detailed photographic and structural inspection of all surrounding buildings to establish baseline conditions. Premiums are calculated based on the proximity of sensitive structures, the total explosive week, and the contractor's historical safety record, reflecting the nonlinear, catastrophic nature of the risk involved. Immediately following the blast, the focus shifts to rapid site remediation and debris management. The rubble pile must be segregated efficiently. Steel reinforcement bars are separated from concrete aggregate using specialized magnetic equipment. The concrete is then crushed on-site into reusable aggregate, reducing transportation costs and landfill fees. This rapid processing is essential because the cost savings achieved by the implosion are quickly eroded if site clearance delays the start of new construction. Effective dust suppression, often involving high-volume water cannons, is critical during the initial hours to comply with environmental air quality regulations. The future of implosion engineering integrates drone-based photogrammetry and artificial intelligence modeling to enhance precision. Drones capture high-resolution three-dimensional models of the structure, providing more accurate input data for FEA simulations than traditional blueprints. AI algorithms are being developed to optimize charge placement and delay sequencing automatically, minimizing the explosive mass required while maximizing collapse control. This technological integration reduces human error in calculation and allows contractors to bid on increasingly complex structures located in tighter urban footprints, further expanding the commercial viability of controlled implosion as a primary demolition method.